Looking at the overview of chapter 12, and this is 12.5, numbers 30 through 32. And so this one we're looking at integration, but we're going to pump the brakes on integration. This is just an introduction to it. This is also still using geometry. So we're simply going to be finding the area of a rectangle, area of a circle, and an area of a trapezoid. It's just to kind of get you an idea so that when you do go into calculus class that you're not bombarded with something that you're completely unsure of and never have seen before. So what's happening here is we're going to be finding the area using left endpoints. And what that means is that we have a function here, 2x plus 4. So I have it graphed here in red. And we have x equal to 1 and x equal to 5. And I have those drawn up here. So we're just finding the area underneath this red line in between 1 and 5. And it gives us this n, and what that is doing for us is telling us the number of rectangles that we're going to be using. So we're going to be using 1, 2, 3, 4. And I know that can be confusing because you go, hey man, we got a 5 here. Shouldn't we have 5? Well, we're not using here from 0 to 1. So we're only using 4 of them. And we're going to be using 3 different types of rectangles. So the first one where we start at the left-hand side, and I have this, the work is done in red here. And what happens is we're starting with the left side, meaning we're using 1, and we're using the length of this side as our rectangle as well as the distance across here. All right, so that's what we're using. And so when we have the area of a rectangle, we have base times height. And so in order to do that, we start from here and we'll draw it out to 2, and then we'll draw one from 2 out to 3, and then from 3 to 4, and from 4 to 5. And so what can be confusing about this is like, well, I have 5 values here. How come I'm only plugging in 4? And that's why we have this n equal to 4. So we start with the furthest most left, 1, and we're excluding the furthest right. So you won't see an f of 5 here. So we simply plug these in. And since our distance between 1 and 2 is 1, we kind of miss that here. So 6 times 1, 8 times 1, 10 times 1, and 12 times 1 for the area of that rectangle. And then we just add up these values after we plug them into the function. So 36 represents the area using the left endpoints. And then we're going to do that same process for B using the right endpoints, which means we're starting at the right. So I'm starting at 5, and these are called, they're inscribed and circumscribed. So the first ones we did starting from the left are circumscribed, and we have, inscribed, meaning we have a little bit of area that's not accounted for. And then circumscribed is above the graph. So it's the approximation is going to be a little bit more than what it actually is. So we start from the right, we go to the left, from 5, and then 4 to 3, 3 to 2, and then from 2 to 1. And so in this one, we won't see an f sub 1. So on the furthest right, we start with here, and we exclude the furthest left. And so f of 5 gives us 14. And we've already done the work for f of 4 and f of 3 and f of 10. So I just copy those answers down. And once again, we add those up and we get 44, and that represents the approximation of the area of the curve on the right-hand side as the endpoints. Then for C, all we're doing is finding the average between those two. So 36 plus 44 is 80, divided by 2 is 40. And then the midpoints, this is the third way that we're doing it. So you're actually taking the average in between there. So instead of using 1 and 2, we take the average in between there, which is 1.5, and then the average here is 2.5, 3.5, and 4.5. So we're plugging in those values, and so that's taking, we're writing a little rectangle here that's going to include some above and below. So it's going to cut this in half. And so as you can see, since we're dealing with a linear equation, that's also the same answer. So as I plug in 1.5, I get 7, I get 9, I get 11 and 13. I add up those and I get 40. So it seems like a very complicated way of simply just finding the area of rectangles. On to 31. Looking at this, it might not be as obvious that we're looking at a circle here. And so we have y is equal to this function that's given us, the square root of 4 minus x squared. We square both sides, we get y squared, and we move the x squared over by adding. And so here we see the formula of a circle. So y squared plus x squared is equal to r squared. And since we're not adding or subtracting anything at y, that means our center of our circle is at 0, 0. And we take the square root of 4 and we get 2, and that is our radius. So if we see this beautifully drawn circle over here, We can see this is the circle that we're talking about. And this here in red, this is called, and this is, we're using integration here. And so this is saying we're evaluating this from -2 to 0. So I also wrote this in red from -2 to here. And so we're only looking at 1/4 of the circle. So to find the area of a circle, we use pi r squared. We plug in our radius of 2, and we get 4 pi. Since we're only looking at this green part here, we just divide this by 4, and we get pi. Going on to our last problem, 32. Here we're going to be using the trapezoid method. And to find the area of a trapezoid, we have the height times the sum of base 1 plus base 2, and all of that is divided by 2. And so we're given this function and we're given this integral. And so in order to find h, we simply subtract the s, or the 7 and the 4. We get 3, so now we know our h is 3. And then for each of the bases, we just simply plug in one of those endpoints. And so here we have base 1, all I did was plug in 7, I got 16. And in base 2, I plugged in the other one of 4, and I got 10. So now I know our base 1 and base 2. And now I just plug in these values into the equation. Math happens, and we end up with 39.